So in this question, we are given an aluminium alloy, right? So it means the material is aluminium, right? And it transmits a 30 HP, um, 30 HP, right, at 1200 revolution per minute, right? Now, using a factor of safety that is equal to 2.5 with respect to yielding, we need to determine the smallest diameter shaft, right? Smallest diameter shaft that can be selected based on the maximum shear stress theory. Um, and the yield stress is given to us that is equal to 10 ksi, right? So let's start with the solution. Now, let's start with a solution. So example 5.6 is great for helping us with this problem, right? Now, first of all, what we are going to do is that we start by transforming the power, transforming the power and the angular velocity, angular velocity in foots per pound, right? In foots per pound, sorry, in foots pound per second. Per second and radians per second, right? Just as it is done in example 5.4. So it means that power would be 5 HP into 500 feet pounds per second divided by 1 HP, right? That would be equal to 16,500 feet per feet pound per second, right? Next, we need to change the angular velocity. So that is 1200 revolution per minute, right? So 2 pi radian divided by 1 revolution into 1 minute divided by 60 seconds, right? So this would be equal to 125.66 radian per second per second, right? Now, next, using equation 5.10 to find out the torque, right? So, torque is equal to power by the angular velocity. So, that is 131.3 feet per pound, right? Now, don't forget that this torque is in feet pound, meaning that when we use it to find the radius, in inches and we have to multiply it by 12, right? Now moving forward, in chapter number 5 we saw that torsion creates only shear stress, right? Only shear stress, and it can be found by equation 5.7, right? So because we are interested in the maximum value, now it means that the shear stress is equal to divided by j, right? Now for cross-sectional area, j is equal to pi by 2 c raised to power 4, right? So this can be rewritten as this, that shear stress is equal to 2t divided by pi times c raised to power 3, right? And when we'll solve it for c, we'll get that it is equal to cube root 2t divided by pi times the shear stress, right? So Now this above equation is the one that we'll use to find the radius, right? And since we only have the torsion, so the only stress is the shear stress, meaning that the stress in the x and y direction is equal to 0, right? Now what we're going to do is that we're going to use equation 9.5 to find the principal stresses, right? So let's use it. Now again, I'm going to do the math for the principal stresses together, and in the end I'll um, deal with them separately, right? So I have sigma sub x plus sigma sub y divided by 2 plus minus under root parenthesis sigma sub x negative sigma sub y square plus the shear stress, right? Now, since this is the case, right, there is no stress in the x and y direction, so it means that this would be um, cancel out, right? And so this one, right? So it means that we'll be only having the shear stress, right? So not doing plus minus and the absolute value, right? So for sigma sub 1, we'll be choosing the positive value, right? So, and for the sigma sub 2, we'll be choosing the negative sign, right? Now it is very clear that the principal stresses have different signs, so it means that in this case, the equation 10.27 states the maximum shear stress theory for this case, right? So that is the real stress is equal to the absolute value of the difference of sigma sub 1 and sigma sub 2, right? Substitute these values over here and we'll get that the yield stress is equal to 2 times the absolute value of the shear stress, right? Now, the material yield stress is given by the problem, right? That is 10 into 10 raised to power 3 psi, right? So, what we're going to do is that the coefficient of safety or the factor of safety, let's call it K, right? So, K is equal to yield stress of the material to the yield stress that we just calculated, right? Um, we need to find out the yield stress, right? So rearrange it. So this would become yield stress is equal to the yield stress of the material divided by K, right? Substitute the values and we'll get that it is equal to 10 raised to power 3 divided by 4 into 10 raised to power 3. Sorry, 2.5. 2.5, right? And that is equal to 4 into 10 raised to power 3 KSI, right? So from here, what we're going to do is that since we have the yield stress now, so we can find the shear stress, right? So the shear stress is equal to the yield stress divided by 2, and that is 4 into 10 raised to power 3 divided by 2, right? So that would be 2 into 10 raised to power 3 KSI. Now finally we can find the radius and from there the diameter, right? Now for the radius we have C is equal to cube root, right? We just calculated all of these equations above, right? So I'm just using them. I'm doing nothing else over here. So that is 2t divided by pi times the shear stress, right? So substitute the values and you'll get that it is equal to 0.74 794, 945 inch, right? And the diameter is equal to 2c. So plug in the value of the c that you just found, and we get that it is equal to 1.5890, and that is approximately equal to 1.59 inch, right? So this concludes our answer.